This is a video covering the Born-Haber cycle, and it also relates to lattice energy. We're going to use this problem as an example. It might be off of your practice exam for Unit 2. But if you haven't seen it before, we have all the data that we need here to do it. The question says, given the data below, construct a Born-Haber cycle to determine the lattice energy of calcium oxide. And the first thing that I wanted to do is I just wanted to talk about the Born-Haber cycle and how that relates to the lattice energy of something. The Born-Haber cycle is basically saying that you're going to go from the elements, so the pure elements, so that would be oxygen and calcium solid here, and you're going to do some work to prepare them, and then eventually you're going to put them together to make calcium oxide. And the Born-Haber cycle is not just about these processes in between, but it's also about the energies of each one of the processes in here, and then also how much energy it takes to make a compound. And then all of these together, so all the energies related from going from the pure elements to the final product is called the delta H of formation. So let's talk about what the individual processes are. What we need to do is we need to take calcium solid and we need to turn it into calcium gas. And then we need to take some electrons away from it so that it produces calcium ions eventually, because out here we want it to be calcium oxide. That's calcium plus 2 and oxide 2 minus. So we need to prepare each one of our elements in that configuration so that they will come together at the end. They'll be attracted to each other. Okay, so the first thing that we need to do is we need to take one electron away. So I took calcium gas that had a 0 charge, and I made it into calcium plus, which is just taking one electron away. And then I'm going to do that again so that I produce the calcium ion there. That's what I need it to be so that they come together. Okay, let's talk about what it's going to take to prepare the oxygen so that it comes together with the calcium. Now the oxygen is going to start as a gas, so we don't need to produce a gas like we did for the calcium. It's just already a gas, but what we do need to do is break it apart into two separate oxygen atoms that are a gas. That takes some energy to do, so we have to break that bond. And then we have to eventually get it to be a -2 ion. That means adding electrons to it. So in this process here, I'm going to then add an electron so that it makes O minus. And then I'm going to add another electron so that it makes O2 minus, like that. And once I have that done, then I can take these two and I can make them into calcium oxide. Okay, I want to talk about what each one of these processes is called. Anytime we're taking a solid and making it straight into a gas, we call that the sublimation energy. There's an I in here. And it takes energy to make that happen, so that's going to be a positive number. When we take something that has a 0 charge and we make it into a positive ion, we're taking an electron away. And when we take an electron away, that's called the ionization energy. And for this problem, we actually had to do it twice. We had to do it once here, and we had to do it once here. So those are both ionization energies. The difference between them is this is the first ionization energy, and this one is the second ionization energy. All right. And I'm hoping that ionization energy makes you think back to our periodic trends. And that was one of the periodic trends that we learned about on using our periodic table. All right, for the oxygen, when I take something and I split it apart, that is called the bond dissociation energy. And the next one is I'm taking an atom and I'm adding an electron. That is called the electron affinity. And so this is the oxygen getting its first electron, and then the second process is it getting its second electron. So I'll need to be able to find 2 electron affinities for the oxygen, for this oxygen, and then for the oxide ion. Okay, and then when I take my 2 ions and I make them into a compound here, that is called the lattice energy. Now the way these all work together is that each one of these energies is something that we can look up or find, but they all add up to be the delta H of formation. And so what I'm going to do is I'm just going to label them so I don't have to write all the words again. I'm going to label this one as 1, this one as 2, this one as 3. My lattice energy is going to be 4. My bond dissociation energy is going to be 5, and my electron affinity is going to be 6. And how they all add up is basically 1 plus the second process plus the lattice energy, plus the second ionization energy plus the lattice energy plus the bond dissociation energy plus the electron affinity. All those add up to be the delta H of formation of calcium oxide. Okay, so now I'm going to go back and relate this information back to our problem. Just kind of rereading the problem here, it says, given the data below, to construct a Born, use the data below to construct a Born Haber cycle, determine the lattice energy of the calcium oxide. And I'm looking at this information here and kind of the processes that are over here. What I'm seeing is that, look, it's giving me like each one of these. So that is the sublimation energy. That is the first ionization energy. This one is the second ionization energy. So it's giving me each one of these. The very last one here, that's calcium and oxygen coming together to make calcium oxide. That is the delta H of formation. Okay, it's basically taking my reactants and making my product. So let's use these processes and these numbers that are given over here to put them in. So we're going to kind of look at these numbers and we're going to decide which one goes in each one of these 1 through 6 places, or the formation, delta H of formation of calcium oxide. Okay, looking at this first one, that's taking calcium solid and making it into calcium gas. That matches the sublimation. So that is going to be number 1 here. So I'm going to actually write that energy in. This is 193 kilojoules. So the sublimation energy is 193 kilojoules. All right, process number 2 is this one here, taking calcium and making it into calcium ions. When I'm looking up at my problem, that looks like this right here. So this energy is going to be the ionization energy. So I'm going to add that in for number 2 kilojoules. Okay, the next one, process number 3, was taking the calcium 1+ and making it into calcium 2+. And I'm looking down on my list here, and it looks like that guy right there. So taking calcium 1+ and making it into calcium 2+ takes 10 10 kilojoules. The next one on my list is number 4, and that's actually the lattice energy right here. That's the one I'm looking for, so I don't have anything to put in there right now. So I'm just going to write plus number 4. That's kind of like the X in this problem. Okay, going on to the next one. Number 5 is the bond dissociation energy. This is how much energy it takes to break apart an oxygen gas molecule to make single oxygen atoms. When I look up at my list, I'm looking for something going from oxygen to oxygen atoms, and the one that I see is this one right here. But look at the way that it's written. I want to go from O2 to single oxygen atoms, but it's written as oxygen atoms going to O2s. So I want it in the opposite direction that it's written. Now remember back when we talked about thermochemistry, we talked about that anytime you manipulate a reaction, you also have to do the same thing to the delta H. So if we're going to flip this reaction so that it represents the one that we want, so if I'm going to take this reaction that's negative 498. If I'm going to write it in the opposite direction, so that's 2 oxygens, I need to flip the sign of the delta H. So whatever I do to the reaction, I have to do to the delta H. And that also is true. I only want 1 oxygen atom. So what I'm going to do is I'm going to cut this in half so that I get half O2 goes to 1. And if I cut the reaction in half, I also have to cut the delta H in half. And so that's how I'm going to write it down here as my number 5. I had to flip the reaction and I had to divide it by 2 because what I was given in the problem wasn't quite what I needed for my process. All right, the next one is number 6, and that is the electron affinity. To find the electron affinity, I'm going to look up at my the information given, and the electron affinity, it looks like I actually need to do it twice, right? I need to do it here, and then I need to do it here. And I have both of those right here. So getting 1 electron and getting another electron. This isn't specific to this problem, but it's really interesting to me that when oxygen gets its first electron, it goes down in energy. So it must have a really high electron affinity, like it really wants electrons, but giving it its second electron actually costs energy. That's kind of, I don't know, it's just surprising to me that that's the way that it works, but it's because of the electron configuration that that's true. But those are the 2 numbers that we're going to use for our electron affinity. So this is getting the first electron, this one is getting the second. And so that's what I'm going to put in for 6. I actually have to put in both of those. It's a negative 141 and then a positive 878. Okay, now I have my 1, 2, 3, my 5 and my 6 across the bottom here, and I also have the delta H of formation. The delta H of formation is negative 100 and negative 635 kilojoules. I got that from this last one right here. So that process represents the delta H of formation. So now that I have all these things, I can do some math to solve for number 4. Okay, so I added up these and I got 1793 kilojoules. And then I added up all of these and I got 986. Okay. So putting things together, I got 2779 plus number 4 is equal to negative 635. And I got that 4, which represents the lattice energy, is negative 3414 kilojoules. So that represents this last process here, making the calcium oxide from the 2 single ions. If you're doing this as a multiple choice problem, that was answer A. So to review, the Born-Haber cycle is basically going from the pure elements and making them into a gas, and then making them into ions. And you would do that for each element. Then when you've gotten them into ions, you would make them into a compound. And this process here represents the lattice energy. And all of the energies together represent the delta, add up to be the delta H of formation. So depending on what you're given, you can be given each one of these processes, and this here, and you could find the lattice energy. Or maybe you're given the lattice energy and each one of these processes, and you're supposed to find the delta H of formation. The idea is basically, given all but one of them, you should be able to find the last one.